Hello everyone, and welcome to our sessions on digital heritage inspection and survey, which are kindly funded by Historic England. This is a programme of 10 sessions for learners of different experiences and backgrounds to find out more about how digital models and digital twins are being used in the heritage sector. There's a WhatsApp group where the learners can co-mentor and share resources too. My name is Linda Jubb and I'm your host today. I'm a Chartered Building Surveyor and Fellow of the Royal Institution of Chartered Surveyors. Our practice, Jubb Clues, specialises in the survey and repair of historic buildings. My co-host today is Kira Greenwood from Christians, the survey company. This is session 2 of our series. Kira is going to be presenting today on the subject of data processing and outputs.
Hi everyone, so I'm back with the second part of the technology session of this course. If you couldn't attend the first session, let me introduce myself. I'm Kira and I'm currently the Director of Operations at Christians, a surveying company. We specialise in digitalising assets, delivering 2D drawings, 3D models, digital twins and many more. I started at the company 9 years ago as a CAD technician and I've worked across various areas of the business. Over the years, I've gained experience in conducting site visits, coordinating access, managing projects and collaborating with clients to deliver solutions tailored to their specific needs and requirements. Please take a moment to visit our website to explore examples of our work and see how we combine multiple aspects of surveying to deliver exceptional results. So we've all slept since last Wednesday, so let's have a quick overview of digital models and what we covered in the previous session. We discussed various data capture techniques and technologies such as laser scanning, photogrammetry and 3D modelling softwares. Digital models bridge the gap between the physical and virtual world, which allow us to recreate structures, buildings and landscapes with precision. These advanced tools, we capture real-world elements in incredible detail. This technology plays a crucial role in industries such as architecture, conservation and design. It streamlines planning, collaboration and decision-making by providing a versatile foundation for creating 2D plans, 3D models and photorealistic visualizations. So in essence, digital models transform the physical world into a digital format, enabling us to interact with and analyse objects remotely and efficiently. So in this session, we'll explore how raw data is transformed into the deliverables that you're familiar with or have worked with before. We'll discuss the techniques used to process raw data into outputs that contribute to fully functional and interactive digital twins. This includes how point clouds are converted into CAD files or 3D models. Additionally, we'll cover the latest technologies and workflows that enable this transformation. We'll break down the workflow stages, explore visualization methods, and examine point cloud processing. Finally, we'll wrap up with real-world applications and use cases. So the foundation of any digital asset is its processing workflow. But before we dive into processing, it's essential to back up all the data collected on site. Unlike Austin Powers, this isn't the time to live dangerously. While we rely heavily on computers, things can still go wrong, so backing up data in at least 2 separate locations can be crucial, whether it's on existing hard drives, cloud-based servers, or other secure storage solutions. Since raw data files are often the largest that we'll work with, ensuring sufficient storage space is vital. When backing up data, it's good practice to organise it into folders that are based on the software that will require each data set. This simple step makes importing and processing much more efficient. As Stuart pointed out in the first session, there's still no single unified platform for model viewing and management. The same applies to processing, so each stage is handled by different softwares depending on its specific function. These individual processes come together in the final stages to create the complete deliverables. So processing data. Let's discuss the processing for all three main stages of a combined digital model: survey control, point cloud, and photogrammetry. The transformation from raw data to a functional digital model happens in 4 stages: pre-processing, model generation, visual enhancement, and delivery. Each stage involves specific techniques that ensure the final model is accurate, detailed, and easy to work with. Raw point cloud data, while highly detailed, is unstructured and unusable in its raw form. Converting it involves filtering noise, segmenting objects, and reconstructing surfaces to create structured, manageable data. Registration then aligns multiple scans to form a cohesive model, improving accuracy and enabling precise analysis. These processes are essential for applications in construction, surveying, management models, and more, ensuring that the point cloud data becomes a valuable, actionable asset rather than just a collection of points. Properly handle point cloud data, survey control data, and images before processing ensures accuracy, efficiency, and the best possible results. So let's break it down. Processing survey control data. Survey control points are critical for ensuring our models are correctly scaled and georeferenced. Here's how we prepare them. We check the accuracy, making sure the GNSS or total station measurements are correct and free of errors. We standardise all the formats, converting coordinates to the same projection and datum systems for consistency. And then we align the data, ensuring control points match the point cloud and images to avoid misalignment during processing. Processing of the point cloud data. So before we can jump into exporting any files, we need to ensure that our data is clean, organised, and correctly referenced. Why? Because raw data, whether it's a point cloud, survey control points, or images, often contain errors, noise, or misalignment that can impact the final model. Pre-processing helps us to avoid unnecessary rework and ensures a smooth workflow. Point clouds are the foundation of many digital twin projects, but raw scans can be messy. Here's what we need to do during the processing. Cleaning and filtering to remove noise, outliers, and unwanted objects like pedestrians or moving vehicles. Registration and alignment, ensuring all scans are correctly positioned relative to each other using common reference points. Decimate and optimize, reducing the file size while maintaining accuracy. This makes processing faster without sacrificing detail. And exporting them in the right format, so choosing a format which is compatible with other softwares such as LAS files and E57s. Processing of photogrammetry models. For photogrammetry models, high-quality images lead to high-quality reconstructions. Here's what we do during the processing. We sort and organise all the images, removing blurry or overexposed images and rename files systematically. We do metadata checks, ensuring the GPS coordinates, timestamps, and camera settings are all correct. We work on image enhancement, adjusting contrast, brightness, and sharpness for optimal feature detection. The image alignment. The software detects the common features across the images to align them correctly. For scaled models, this will be aligned to its corresponding point cloud generated from the laser scan survey. Mesh creation. A dense point cloud is created from matched key points. The point cloud is converted into a 3D mesh surface made up of triangles, forming the structures of the model. The mesh reconstruction is where raw data starts looking like a true 3D model. Triangulation algorithms help build surfaces, while smoothing and gap filling ensures the model is complete and visually coherent. And then lastly, the texture mapping occurs. This is where the high-resolution images are applied to the mesh to enhance realism, Texture mapping transforms a bare bones model into a visually rich digital representation. So once our point cloud data, survey control points, and images are processed, they're ready to be used individually or combined to create a hybrid model. All this processing ensures that we have accurate alignment between the data sets, efficient processing with fewer errors, high quality outputs for CAD, BIM, or visualization purposes. Pre-processing may take time, but it saves us from headaches later in the workflow. By carefully combining multiple survey techniques, we can create final products that are used as a powerful tool for design, analysis, and decision making. After integrating, refining, and verifying the data, processing is complete and we're ready to export the required format and prepare for use. Later in the course, you'll learn how you can use and view these models to obtain their full potential. Let's briefly review the processing stages for the alternative data capture methods we discussed in last week's session, which is the 360 tools. So this method is less accurate, but it's also less time consuming, making it useful for projects where speed is a priority and high precision isn't necessary. Creating a 360 tool from 360 photography includes capturing high-resolution images using specialised cameras or lenses, then stitching them together into seamless panoramas. These images are edited for the colour correction and any distortions are fixed. The panoramas are then georeferenced and linked with hotspots for smooth navigation between views. The interactive elements like labels, audio guides, or videos can be added to enhance the user experience. Finally, the tour is exported and published in a web-compatible format, ready for platforms such as websites or VR applications, providing an immersive virtual exploration. Future trends in processing. Computer technologies support data processing in multiple ways and are continuously evolving at a rapid pace. When data storage is a challenge, cloud processing minimises the need for high-capacity systems while enabling real-time access and processing from anywhere. It also provides scalable processing resources for faster turnarounds, handles large datasets that exceed local computing power, and offers remote rendering and mesh generation for enhanced efficiency. Emerging technologies like AI-driven automated reconstruction, quantum computing, and edge computing are set to revolutionise digital twin creation and management. As these advancements evolve, digital twins will expand into healthcare, urban planning, and energy, driving smarter cities, efficient infrastructure, and improved patient care. The future of digital twins is faster, smarter, and more widespread, unlocking new opportunities across multiple industries. So let's go over our key takeaways of processing data. In the survey industry, data processing techniques come with both advantages and challenges. On the positive side, modern processing techniques allow for the integration of large, complex data sets, enhancing accuracy and providing detailed 3D models, point clouds, and geospatial data. Standardized formats like IFC and OBJs simplify data exchange and improve workflow efficiency. Additionally, cloud computing enables the handling of resource-heavy tasks, offering scalability and reducing the need for expensive hardware. However, there are some drawbacks. High computer demands for processing large datasets can slow down workflows, especially when working with high-resolution point clouds or detailed 3D models. Integrating multiple data formats from different sources can be complex and time-consuming. Furthermore, balancing model optimization with maintaining the accuracy of the data can be challenging. as simplifying models to improve performance may result in the loss of critical details. So in summary, while data processing techniques in the survey industry offer significant benefits in terms of accuracy and efficiency, they also present challenges related to computer resources, data integration, and maintaining model fidelity. So I'm going to hand over to Linda for discussion time.
Hi, Kira. I'm blown away. That was amazing. Thank you. I'm just having a quick look in the chat to see whether we've got any questions there. At the moment, no questions. I've got a question actually, Kira. You're going to have to help me with this. Please, can you tell me a bit more about how decimation works? I think I understand it, but I want to just hear it again.
Yeah, so decimation is the act of reducing a file size from unnecessary points or just reducing the size of a point cloud. So in each scan, when you're laser scanning, the laser scanner will collect millions of points, and each scan will need to be overlaid in the registration process to allow for alignment. But this can cause like loads of overlapping points, which can be unnecessary. So when you decimate, you can choose the distance between each point. For example, 1 millimeter, 10 millimeters, 20 millimeters. The larger the distance, the less detail you'll get. But it can be handy when trying to reduce the file size to bring into another piece of software or just using it as a cleanup tool.
Right, so if I understand that correctly, you overlap 2-point clouds, and by coincidence, 2 points are like a quarter of a millimeter apart. So there's no additional data from having those two. And so they should be together because, you scan the same object from 2 different angles. So decimation, presumably this is a machine function, decides for you that one of those points is not required and deletes it so that you just simply have less data.
It's almost like an algorithm system that picks out, you can either choose it on a grid system, so you can choose that the grid system allows only 1 point per millimeter, or you can choose it on a randomized system, so each point just has another point within a certain distance from it.
Okay. Yeah, because that's a very clear instruction to the computer, either do it this way or do it that way. And I thought the place where the AI might kick in is if it was starting to detect a surface, it would also, by statistical analysis, decide actually that point's an outlier. That one's more likely to be incorrect than these other 15. And the AI will therefore actually not just reduce the data, but clean it in the sense of try to automatically reduce the number of errors. And the difficulty with that is that if we don't teach it to do it properly, if the AI doesn't have a proper learning algorithm underlying it, that it will start stripping out the very thing that we wanted, which was, but we want this very detailed and bespoke model that takes into account things that we didn't know were there, but we can only pick up with the scanner.
Yeah, it may be also the case that the laser scanner's caught a bit of dust or a fly that's flown past or a tiny little bit of something that's then in the middle of a room. So that point is actually part of the model. So that's why the pre-processing is important, to just check the model, go over, decimate any outliers, like you say, and look for these little points that could possibly cause issues down the line. So that's why it's such an important point, and why the survey industry are kind of expressing that there is a processing time for data, because we look into these small details to fix any issues that could occur later on.
Yeah, so I think in terms of research directions in future, we need to talk to some of our friends who are doing this kind of research to see if the AI would actually maybe go more like an assistance model to help you do the data cleaning, rather than just to run algorithms that just strip out
that would be
duplication
good.
and heavy detail, because obviously our other objective, as you say, is to make these data sets more agile for loading, for storing, for archiving, and for interpretation. Gosh, that's a lot to think about. I'm going to let you go on because there is a question in the chat room, but I think, given what I know about what's coming, that I'm going to deal with your question, Trevor, if I may, in a moment, and let Kira take us through the next step in terms of processing.
Yeah, that's absolutely fine. Yeah, it's a big one, I know. Thank you.
I know, Trevor. I'll be back with you in a mo. All right, back to you, Kira. Thanks so much.
Thanks, Linda. Okay, so exporting and deliverables. Now we've collected our data, we've processed it, we've got it to a point where we're ready to export it to then move that on. So digital models can generate a vast range of outputs that are essential in the survey industry. These exports help professionals analyse, measure and visualise real-world environments with high accuracy. So first we have point cloud data, which provides a dense set of 3D points used for mapping and modelling. Then there are 3D mesh models, ideal for visualisation and simulation purposes. For aerial mapping, we use orthophotos, which are high-resolution georeferenced images that provide a true-to-scale representation of an area. When it comes to elevation data, we can extract digital elevation models, DEMs, DSMs and DTMs to analyse terrain, create contour maps and support flood modelling. Speaking of contours, there's then DXFs or shape files for CAD and GIS applications. Additionally, volume calculations and reports can help track material quantities for stockpile management and earthworks planning. For infrastructure projects, we can extract cross-sections and profiles, while textured 3D models provide a visually detailed representation for urban planning and heritage documentation. So ultimately, digital twins don't just create a 3D model, they can produce valuable, versatile data that can be used across multiple industries, making it such a powerful tool. So let's talk about what ortho images are and what ortho stands for. So they can be an integral part to a building analysis, as Linda mentioned in her past case studies prior to session 1, because the term ortho comes from the Greek word meaning straight or correct. So in surveying, ortho refers to orthorectified images, which means they've been geometrically corrected to remove distortions caused by camera angles, terrain variations, and lens distortions. This correction ensures that the scale is uniform, making ortho images highly accurate for taking measurements. Now, where do these images come from? So we can extract them in 2 ways, and we've got both examples on the screen. So we can extract them from point cloud data by projecting the points collected with the laser scanner onto a 2D plane and applying colour values. We can generate an ortho image that maintains real-world accuracy. And we can also extract them from a photogrammetry model. So once the model is built, software generates orthophotos by correcting perspective distortions, stitching images together, and ensuring spatial accuracy. The key advantages of ortho images is that they allow surveyors, engineers, and planners to take precise measurements directly from the image. Just like a map, whether derived from point cloud data or photogrammetry, they provide a highly detailed, accurate, and scalable representation of the real world. And it's important to note that if these need to be related to the building that has been measured, they must be shown with an appropriate scale bar for reference. So you can see the difference in the 2 ortho examples on the screen. You've got the point cloud data, which, because it's a ground-based tool, the laser scanner, you've got all the angles from the ground-based position, and it the information diminishes the further up it goes. But that's where the photogrammetry processing and data capture come in really handy, because it captures all elements from above, So it kind of creates a complete data set. So why are web share files and 360 views so valuable? One of the most powerful ways to make use of a laser scan data is by exporting web share files and 360 views. These allow us to visually explore a scanned environment, offering huge advantages for both technical teams and clients. These exports create a fully navigational 360 virtual tour of a scanned building or site. Users can move through the space as if they were physically there, making it easy to access layouts, conditions, and measurements remotely. They provide support for CAD and Revit teams instead of relying solely on 2D drawings or point clouds, meaning that they can cross-check details, confirm dimensions, and reduce site visits, improving efficiency while preparing drawings and models. Clients can receive a realistic interactive representation of their project, helping them visualise designs before construction or renovation begin. And this makes presentations and approvals more engaging and easier to understand. WebShare files and 360 views are especially beneficial for people with disabilities who may have difficulty physically accessing a site, and these tools will allow them to virtually navigate through the spaces, supporting inclusive decision-making in projects. So in short, exporting WebShare files transforms laser scan data into an accessible, interactive, and highly valuable resource, whether assisting CAD and Revit teams, enhancing client engagement, or promoting accessibility. These tools bring huge benefits to the surveying and design process. So once we've exported the information that we want, we then need to integrate the data into different softwares. So now that we've covered the data collection, processing, and possible exports, let's move on to the next step, integrating the exported information into softwares like AutoCAD and Revit and looking at possible outputs. This process allows us to transform the data collected into usable, precise deliverables tailored to our clients' specific recommendations. As a company, we've dedicated significant time and effort to developing seamless workflows for integrations like these. The way data is exported determines how it's brought into the next software, ensuring that it remains aligned with the correct coordinate system and maintains accurate measurements. Creating 2D drawings from an existing building requires the use of orthographic images to ensure accuracy in replication. These orthos must be exported and then imported into software like AutoCAD, where they can be traced and converted into precise drawings. When importing an ortho image into CAD, the first step is to ensure it is correctly positioned in the real-world coordinate system, if this is a required part of your specification. This is done by inserting an ortho image, choosing the correct scale, and ensuring that the CAD project is set to the same coordinate system as the ortho image to maintain accuracy. Once the ortho image is correctly placed, we can translate it into a detailed 2D line drawing. By using polylines and layers, we trace important elements such as walls, doors, windows, or service features. We can apply layers and line weights to organise elements for clarity and easy editing. Or we can add hatches to help differentiate between materials or surfaces, while text and dimensions provide additional information. The drawing is refined and exported as DWGs and PDFs for use cases such as design, planning, or heritage inspection. Another way to digitalise a building is by creating a 3D model from the survey data. These models can be developed using softwares like Sketchup, 3ds Max, and Rhino, but the most widely used building modelling software is Autdesk Revit. Revit is more than just a 3D modelling tool. It also enables building information modelling, which is what BIM stands for, enhancing project coordination and data management. Let's firstly discuss the process from point cloud to BIM model. So we export our process scan data as an RCP, a reality capture project, one of the previously listed exports, which is compatible with Revit. The RCP file is imported into Revit. Unlike CAD, Revit has a limited working space, so the project base point must be aligned with real-world coordinates to ensure proper positioning within the workspace. It needs to be aligned and scaled, checking that the point cloud is correctly aligned in the real-world coordinates, ensuring accuracy throughout the BIM model. Using the point cloud as a reference, we begin tracing and modelling walls, floors, windows, and structural elements to replicate the building in digital form. As we build the model, we integrate metadata such as materials, asset details, and construction elements to enhance the intelligence of the model. Unlike industries like architecture, where designs are created from scratch, we model from as-built survey data. By integrating laser scan data into Revit, we can produce highly accurate, information-rich digital twins of real-world structures. This enhances decision-making, minimises errors, enables clients to better visualise and manage their buildings. So BIM integration. So measured surveys are essential for recording the conditions of existing buildings and sites. We use the survey techniques discussed to collect highly accurate spatial data, which forms the foundation for creating an as-built model, which can be used for BIM implementation to take the model to a new level for renovations, restorations, class detection, project planning, inspection purposes, and many more. So what is BIM? BIM, or Building Information Modelling, is a process that involves creating and managing a digital representation of a building or infrastructure. Unlike traditional 2D drawings, BIM models are intelligent, data-rich, and allow for real-time collaboration between architects, engineers, and surveyors. BIM goes beyond just 3D modelling. It integrates information about materials, structural elements, and life cycle data, making it a powerful tool for design, construction, and facility management. In session 7, it will be discussed how these models are used and how they enhance the understanding of buildings and structures. Okay, I think Linda's got a poll for everyone now.
I'm going to ask a very difficult question. Now, so far, we haven't had any hard questions. And I'll give you a clue that I don't actually know how I'm going to answer this myself. Do you think digital models and digital twins are different things? And I've given you 4 different answers to think about carefully. And as I say, I haven't really jumped in yet myself. They all feel viable to me.
Yeah, it's a hard one. It's not as clear as what everyone thinks, I don't think.
Well, it's good, Kira, because only about 12 people, about half of the room has voted at the moment. So the other half is really rubbing their chin now quite hard about this. Now we've come in with one on the no. That's a very confident no there. No, a slightly confident no. I'm going to let everybody vote, and I'm going to insist that you do. Jack's come in and said, yes, it's not obvious what the difference is.
Yeah, I was just going to say I'd like to abstain from voting because I think it's somewhere in between. I can't explain it and it's obvious.
Well, 0 abstentions because I'd rather it was a mood vote.
I can explain it. I can explain what I think the difference is. Whether or not that's correct is another question. But I don't necessarily think that the explanation is an obvious one. So what should I put? I think I'm going to have to go for the top one, aren't I, for now? But yeah, if I was being pedantic, I'd like an extra.
Are you going to come down on that? Well, you know what? I was hoping, Jack, that there would be somebody who was so sure that they knew what they were doing that I could ask them to describe their thinking, and you've therefore volunteered yourself. But let's just see how this ends up, because I'm going to insist that you all vote. So we're only at 23 of 29 now. I noticed that 2 people left the meeting. 2 people left the meeting because they didn't feel like voting with I've asked too much of them. Either that or the signal dropped out for them. I'm very sorry. Ian, you've come in with a suggestion here. Ian says he thinks a digital twin is one sort of digital model, but not the other way around. Interesting. Like all thumbs are fingers, but not all fingers are thumbs. Oh my goodness, this is getting quite deep. Thank you, Michael. I like it. So we've got 25 out of 29. Come on, whoever you are, you other 4, do please vote. That might be me, you, and Kira. Who's
I've
number 4
voted.
there? You voted. Oh, come on, more votes. And Vivek says a twin is more advanced than a digital model. Down to 28. I'm going to stop harassing you then, because otherwise everybody will have left the meeting. So I'm going to end the poll. We'll close it here. And that was the result there. More yes, they're different than no. Okay, Jack, do you want to pile in and tell me how you voted and what you thought?
Not particularly, but I'll give it a go. So I feel like a model can be several different kind of interpretations of a building on a software, whereas a twin is much more. It's a twin. It's much more not necessarily accurate, but yeah. And again, I don't know. That might not be correct, but that's just looking at the 2 different words. I'd say a model could be several different things with several different levels of accuracy, looking at different things, whereas a twin is more of a like for like kind of replication of the entirety of a building. But again, I don't know.
Okay, I'm going to bring in Vivek at this point, who's been a great participant. Vivek.
Hi, can you hear me?
Yeah, I can hear you.
Yeah, so I think the digital model is like a preliminary study model, like how we do. It can have a basic a shape or something, but when you start putting more properties to the certain elements, then that's how you replicate the reality, and it becomes like more digitally advanced model, like putting up those material properties or maybe different parameters to control those properties. I think so.
Yep, I agree with that. Rich Aylesby. You there, Rich?
Sorry, I was just typing. Yeah, I think in my understanding, it's to do with the time-based and the in terms of being an interactive model.
Okay, so like real-time data as well as geospatial.
Yeah, exactly. And it's the complexity of it. So therefore, obviously, a twin is much more complex because it's reactive to the surroundings and reactive to information that's coming in all the time, whereas the model is more, I mean, if you, for example, have a 3D CAD model of a car, that's sort of fixed in time with all the data points that's gone into it, as opposed to a car that's driving around with sensors on it, which is updating, which is more of a digital twin. That's my interpretation anyway.
Cool. You made that very clear, actually. That's useful. Brahim.
Yes,
Here he is.
you heard me?
Yeah, gotcha.
Hello, everyone. So I think that the difference between digital twins and digital model is the real-time updating. So you can, in the digital twin, you can add information and everything it's connected. But in the digital model, it's like Sketchup model. You finish the model, you haven't information inside this model. So the interaction between inside the model, it's the difference between the twin and the model.
Right, I agree with that. One being sort of finite and the other being ongoing. Although we have talked about how your digital model is buildable in as much as it isn't finite. You can build on it. Now I'm going to have to be forgiven for my pronunciation, but I'm going to go for it anyway. Jialu.
Oh, hello everyone.
Hi.
I don't know if my comments is correct or not. In my opinion, I think digital twin is more related to the like real-time data, and for your digital model, may not relate to real time, which is I think a digital model is like falls under the broad umbrella of a digital twin, and digital twin also can do a lot of integrations. So, but as I mentioned, I don't know if that's correct or not.
Okay, have we had Ian yet? Ian Harrison. I like Giano's explanation. Ian Harrison, are you there? To APIF, what do you think? No, we haven't got the line with him. He may be on without microphone. Stuart. Stuart Wright, please, your opinion.
Yeah, hi, sorry, I was just trying to
Hi,
find...
there you are. Yeah, I'm going to stop this share. Go on.
Well, I've always seen it that the digital model is about the software, and the twin is a concept of something that you interact with. That's my perception.
I'm really glad you used the word concept, because Kira and Thomas Whitehead from her office and I had a bit of a discussion about this on Monday, and we did decide that digital twin as a noun is a bit like school. It's more of a concept than a sort of physical thing, or a defined thing. So when you see a school, you know it's a school, you understand it completely. But the concept of a school doesn't necessarily need a physical representation. It doesn't have to take a particular form, such as the Arts and Crafts School of Architecture or whatever. It can be conceptual as well as having a materiality to it. My own feeling was a bit more like, I think it was what Ian has said, and to some extent what Vivek was saying, was that the digital model is a component of a twin, in as much as I almost think about those initials BIM, BIM. You need building, you need some kind of physical thing, otherwise you can't copy it. And then you need information, which is stuff which isn't just the geospatial stuff. It's a bit more to make a twin. And then you need the M is the model, but you do need a geospatial representation as well. And I suppose what we're exploring on this course is, how do you get that geospatial representation, and what are you going to use it for? What kind of information will you put on it? And the given is that we've got a heritage asset to start with, and that's slightly different than the original concept of BIM, because of course BIM was for new builds and for projects that didn't exist. I suppose they've always had models, like architects' models about what is coming as a sort of scale representation of what it might look like in 3D. That's the 3D aspect of it. But for our sector, they are twins to the extent as there's a real world version and there's a digital version, and they are very much alike. So the issue of time, real time information, sensors and so on.
It sounds like we're trying to oversimplify it, and actually most of the things people have said are true at the same time.
Yeah.
And if you came up with a shopping list of items underneath the definition of each, a lot of them would be relate to what most people have said.
Yeah, I agree, Stuart. I think like what everyone has said is effectively correct. But if we're defining a digital twin by it having real-time information, but then we took away the visual aspect, so you couldn't, it was just like a white model with the real-time information in it, does that then take it away from it being a digital twin, because it doesn't physically, you can't see the bricks on it? So I think it's just a phrase that people have extrapolated out over multiple different things. It's kind of lost its meaning, but has multiple meanings at the same time.
Very good. That makes me want to loop back to the question that Trevor raised, and I'm sorry for parking it, Trevor, but I think when Stuart's used this phrase shopping list, does that help with your question about how these things are costed, you know?
Probably to a certain extent, yes. And I know it was never, you know, it's never going to be a straight answer. And I guess every project is very specific and what the client needs. And yeah, so I just wondered what the kind of scale of the fees or the costs of doing this type of work is. Just, you know, I've got absolutely no idea. But I imagine there's a lot of new people who, you know, are new to the topic, probably curious.
What we might do is we might do later there is part of this course where we talk about procurement and business case and so on.
Mm-hmm.
And in between, there is going to be a bit of a focus on specification, standard specifications, and using them like a tick list so that you can build up all the things that you want. There are people in this group who are absolutely dead certain, unless this model that you've got is dimensionally accurate and very accurate, you're not providing anything new. And then there is this other sort of group of us who are, you know, to some extent, well, we're not geospatial surveyors, and, you know, we're using things like Google Earth and models that are, you know, use case specific. They've got a specific use case where the geospatial aspect isn't the most important thing. So I would say bear with us while we go a bit further into this, and then we can maybe there are also building owners and people commissioning models in this group, Trevor. We maybe do a bit of a role play about how we do that. Define what the use case is, try to think what a whole shopping list would look like, how we rank what's essential from what's desirable, and therefore arrive at something that suits the user. Because, as you know, in the real world, people come at this the other direction anyway, because they just come with their budget and go, well, I can't afford that. So all of the briefing in the world won't make any difference if they simply haven't got the budget to do it. Righto, I'm going to step back for a minute and allow Kira to finish her presentation, but I found this conversation really, really useful for me in my thinking. I'm sorry, Marius, you had a contribution there. I can see in the chat, just bear with me. Yes, I agree with that as well. That's been shared. Okay, back to you, Kira.
Okay, thank you. It's the chat. Okay, so let's look at the key takeaways from the outputs that we can derive from the data collected. Creating a timestamp of a building or a structure in its current condition in forms such as CAD drawings or revit models are essential for disaster recovery, maintenance, compliance, and future planning. In emergencies, they can provide accurate structural data for rapid damage assessments, efficient reconstruction, and insurance claims if needed. They also enhance facility management by streamlining maintenance, asset tracking, and repairs. Compliance with fire codes, accessibility standards, and historical preservation is easier with up-to-date documentation. Additionally, these models support future renovations and expansions, enabling precise planning, clash detection, and sustainable upgrades. So by maintaining an accurate as-built record, buildings can remain safer, more efficient, and adaptable for years to come. So this is a case study of a digital twin, which we now have learned that we don't actually have a defined definition, but we know that it could be a combination of models, which Christians have surveyed. So digital twins can be defined in various ways, but at their core, they are just digital representations of a building or structure, which can provide a mix of accurate visual models, measurable distances, integrated data, offering valuable insights to inform users about the key aspects of the building. This case study details a bridge survey conducted for a client to assess its structural health, particularly in hard-to-reach areas. To ensure accurate positioning, control points were established around the building, aligning it with a real-world coordinate system. The structure was then scanned from all accessible positions on foot, producing a precisely scaled model that enables accurate distance measurements. A drone survey was carried out, capturing high-resolution images from multiple angles to generate a true-to-life digital representation of the bridge. The resulting deliverables enabled the client to conduct a detailed desktop survey, identifying even the smallest defects. This facilitated markups for repairs, condition reports, and structural engineering analysis. With this information collected, it can be utilised for future surveys, extending the data's life cycle and enabling the integration of new developments over time. So this model now can then move forward into becoming more of a twin. Things like monitoring sensors can be attached to the bridge, which can be linked back to the digital model, which in turn extends the life cycle of the model. So the data processing and outputs, key benefit takeaways. To wrap up, here are the key takeaways from today's session. First, processing techniques are essential for turning raw data into useful, actionable models. Second, effective visualization makes these models accessible and impactful. CAD technology enables scalability, while BIM adds the intelligence needed for advanced analysis and monitoring. And finally, the future of digital twins will be shaped by emerging technologies like AI and real-time edge processing. These developments will unlock even greater potential across industries.
Yeah. I want to actually ask Kara, did you use any drones for the photogrammetric survey? Or if so, could you share how you planned the drones' flight paths to ensure comprehensive imaging collection?
Yeah, so were you here for session 1 last week, or have you started this week?
Last week, this week, okay. This week, both are okay.
Okay, so last week we went over the different data capture methods for photogrammetry models. So you can re-watch last week's session if you want, when Linda uploads it and shares it to everyone. But we discussed the multiple different ways, so using ground-based photography with cameras, and also the use of poles. So for any higher up areas which are hard to reach, we've got the cameras mounted to a pole. But also the importance of using drones for photogrammetry to gain all the data that we can't necessarily reach by hand or with a pole. And these are done with the drones, with the cameras mounted to the drones, and they can be used for mapping purposes as well as just really high buildings, roof data, behind parapets, all that information that you wouldn't usually get. So regarding the flight planning, I personally don't do that myself. So we have a team of UAV pilots, and they run all the flight planning, but I believe that it's done through a software. So they will input the information of the building or the mapping area, and then the computer software actually generates a mapping plan, is what I believe, and then that is ensuring that every angle and all the images collecting are covering everything that you need to capture for the photogrammetry model. Does that make sense?
Okay, thank you.
Oh, we're going to do a little bit more on that because we've got a case study next week. So first of all, please, if you could all join me with little clapping emojis, and we've already got some people who've been very kind in the comments, Kira, to say thank you so much. I'm personally so grateful to you. It's amazing what you've done, and I'm really grateful. Next week we've got another presenter coming, which is Tom Martin from Man Williams Structural Engineers. They're care accredited engineers, and they're going to do a case study with us, where we go into a bit more detail. Some of those questions around the drones and so on will be answered next time. So I'll see you next week. I'll send out an invite in due course. And also, if you can join us in the WhatsApp group, that'd be amazing. The number's there on the screen. Thank you so much, and bye-bye, everybody. Thanks, bye.
Everyone, bye.